In this unit, we're going to explore the reactivity and structure of alkenes, an organic functional group containing a carbon-carbon double bond. Alkenes are highly useful as starting materials to complex organic molecules because the carbon-carbon double bond is nucleophilic. Specifically, the pi bond, the pi electrons, are nucleophilic. And unlike SN1 and SN2 reactions, where we're only changing the structure really at one carbon, right? The electrophilic carbon picks up a nucleophile. In reactions of alkenes, we can often add groups at both carbons of the alkene. These addition reactions lead to relatively highly functionalized products, right? I can put a functional group here, and this leads to more structural complexity and greater diversity of products we can make with addition reactions of alkenes. So these addition reactions are going to be our focus in this unit, and they'll primarily involve the addition of an electrophile to the alkene, since the pi electrons in this carbon-carbon double bond are intrinsically nucleophilic. We're going to start with the foundations of what an addition reaction to an alkene is, look at common reagents that add to alkenes, and we'll talk about addition reactions in thermodynamic terms, noting that addition is the reverse of elimination. So there are some thermodynamic considerations here, particularly considering we've already seen elimination reactions. So to do the reverse of elimination, we need to make sure that that's thermodynamically viable, and we'll see that it is in many cases, particularly when we choose the right reagents. We have regioselectivity and stereoselectivity issues in alkene additions, sort of analogously to what we had in elimination reactions of alkyl halides. And so we'll need to consider these factors when predicting products of reactions. And we'll dig into a variety of specific reactions here in this unit. Hydrohalogenations, where we're adding a hydrogen halide like HCl or HBr. Hydroboration oxidation, and acid-catalyzed hydration reactions, which add H and OH across a double bond in a very particular way. Halogenations, which add two halogen atoms, one to each carbon of the double bond, as well as halohydrin formation, which is conceptually related to halogen reactions. And others, including hydrogenation, epoxidation, syn-dihydroxylation, and oxidative cleavages of alkenes, all of which involve the addition of atoms or groups to the two carbons of the alkene double bond. Then we'll learn how to apply additions to alkenes in synthesis, taking advantage of the fact, again, that these alkene addition reactions often densely functionalize organic molecules, putting two functional groups right next to each other in the product. Addition reactions are the reverse of eliminations. We've previously seen, for example, that when Y is a hydrogen and X is a halogen, loss of Y and X produces a carbon-carbon double bond. This is an elimination process in the reverse direction. In the forward direction, X and Y can add to the carbons of a double bond, X and Y coming from whatever reagents we use, to produce a product with two functional groups adjacent to one another. And in many cases, neither X nor Y is a hydrogen. So we've got two functional groups right next to each other at two tetrahedral carbons in the product. So there's some stereochemical issues here as well, if you think about it. This is very clearly achiral, being planar. But if these groups are different from each other, for example, we could end up with one or even two stereocenters in the product. So we need to think carefully about stereochemistry in these addition reactions quite frequently. More often than not, the reagents we use will be electrophilic or acidic, because the alkene pi electrons are relatively nucleophilic. The alkene is relatively happy to give electrons away. So for example, we can think of the alkene as a Bronsted base, picking up a proton and generating a carbocation. Or we can think of the pi electrons, the alkene functional group, as a Lewis base, with that pair of electrons donated to an electrophile, and a carbocation again forms, but now we have an electrophile carbon bond adjacent to that carbocation. So carbocations are going to be key in many of the mechanisms of this unit, although we'll see some addition reactions that actually avoid formation of a carbocation altogether. Whether an open carbocation forms or not is actually a key mechanistic question throughout this unit. This slide highlights the 6 addition reactions that we'll talk most about in this unit: hydrohalogenation, in which H and X are added; hydrations, in which H and OH, the elements of water, are added; hydrogenation, in which we add 2 hydrogens; halogenation, in which we add 2 halogens; halohydrin formation, in which we add an OH and an X; and dihydroxylations, where we add 2 OH groups to the 2 carbons of the alkene. We'll notice some mechanistic parallels across these reactions, studying the regiochemistry and stereochemistry of each reaction and what that tells us about the mechanism. And our ultimate aim here is to be able to predict the products of these reactions and use them strategically in synthesis. Addition and elimination are mechanistically the reverse of one another. We've previously seen, for example, that if we take an alkyl halide and we hit it with a base, we can eliminate the elements of HX from the substrate and make an alkene. On the other hand, if we hit an alkene with HX, at least in theory, it's possible for HX to add to the alkene, producing an alkyl halide. But with one reaction being the reverse of the other, it seems like one reaction should be thermodynamically favorable and the reverse should be thermodynamically disfavorable. The interesting situation with addition and elimination is that the enthalpy and entropy changes, as we'll see in a second, have the same sign. And so this leads to a situation where we can modify the reaction conditions to promote addition or elimination. If we want to think about the enthalpy change, let's consider the bonds made and broken here. We're breaking in the forward direction, in the addition direction. We're breaking the carbon-carbon pi bond and the HX bond, and we're making a carbon-hydrogen single bond and a carbon-X single bond. And so, in a sense, just very naively, we're exchanging a pi bond for a sigma bond, right? We went from 1 sigma bond and 1 pi bond to 2 sigma bonds. And this is generally going to be exothermic, since these bonds collectively have a higher BDE than these bonds that were broken. From an entropic point of view, it's pretty clear. We go from 2 starting material molecules to 1 product molecule in an addition reaction. And so addition has a negative entropy change. We're bringing 2 things together to become 1. And elimination has a positive entropy change, and we touched on this previously, that elimination converts 1 molecule into 2, essentially. And so we have delta H less than 0 and delta S less than 0. Thanks to the magic of delta G, the free energy change, addition will be favored at low temperatures, where this entropic issue, this issue of a negative entropy change, is less important at lower temperatures, and we're benefiting from the exothermic nature of addition. On the other hand, elimination, although endothermic, has a positive entropy change, so we can make it more favorable by raising the temperature. We can also make it more favorable by including a highly reactive basic reagent that might flip the reaction from endothermic to exothermic. It's quite typical that additions can just be run with the hydrohalic acid or hydrogen halide HX. But alkyl halides won't just fall apart spontaneously on their own to alkenes and HX. We need to use some kind of basic reagent, be that a negatively charged base like an alkoxide or hydroxide, or a neutral alcohol or water, to facilitate loss of H plus and X minus from the alkyl halide. So the upshot here is that elimination is favored at high temperatures and in the presence of basic reagents, while addition is favored at low temperatures. And while we probably won't see many temperatures in this unit and reaction conditions, this is something worth keeping in mind, particularly under circumstances when addition and elimination are reversible. For example, when you put an alcohol in the presence of something like sulfuric acid, addition and elimination become reversible, where the alkene and alcohol end up in an equilibrium that depends on the concentration of sulfuric acid and the reaction temperature.